Hello, welcome to part 4 of these chats about resistor networks. In this one we'll be going through a few examples applying the results that we've derived so far to an increasingly complicated set of resistor networks. So the first one we'll be looking at is probably the simplest one I could think of, which is this one. Two resistors in series. Well, the formula that we derived before tells us that if we have two resistors in series, the total equivalent resistance is the sum of the two resistors. In this case, 1k plus 500. 1k means 1000, so that's just 1500, and I would normally write 1500 as 1k5. Right, does it work? Let's give it a try and see. Here's the network in the simulator. And we can see it at the moment with 10 volts across the resistor network. We've got ground on this side and 10 volts on this side. We've got 6.667 milliamps flowing through. And if we set this resistor to 1k5, yep, exactly the same current would flow through. So this pair of resistors here is behaving exactly like a single 1k5 resistor. 1k5 is the equivalent resistance. Okay, next. We've now got three resistors in series. Now, we have derived a formula for three resistors in series, but rather than use it, I want to analyze this in a slightly different way. We've got three resistors, a 1k resistor there, a 500 ohm resistor there, and a 3k3 resistor here. Now, we could consider that those two resistors were our two-terminal resistor network. And we know from the formula we've just used before that the equivalent resistance of these two resistors in series is a single 1k5 resistor. We can replace both of those with a single 1k5 resistor. So, we could redraw the circuit in an equivalent way like this. And now we could consider this as our resistor network. We've got two resistors in series. The equivalent resistance of these two resistors in series would just be the sum of these two resistors, which in this case would be a single resistor of value 4k8. So, we've applied this first formula, adding up two resistors twice. And we've got a single resistor here at the output, rather than applying that formula for three resistors in series. Does this one work? Well, again, we can try that. Here is our resistor network at the top. And if we set the resistor at the bottom here to be our calculated 4k8, then yes, exactly the same current is flowing through our resistor network as flows through our equivalent resistor of 4k8. So the 4k8 resistor is doing the same job as these three resistors in series. So far so good. Next one. I've got two resistors here, which might at first glance look like they're in series because they're in a horizontal line, but looking at where the wires go, you'll notice that they are not. The left-hand side of both resistors is connected together, and the right-hand side of both resistors is connected together. So these two resistors are actually in parallel. We know the formula for two resistors in parallel, and in particular for the case where the two resistors have the same value, the parallel combination of two resistors is just half of the value of either of the two resistors. So the equivalent resistance of this two-terminal network would be just 500 ohms. We can test that one as well. And yes, the same current is flowing out of this two resistor network as flows out of a single 500 ohm resistor with the same voltage placed across it. Okay, we'll move on to a slightly more difficult one. Right, this one. We can no longer just simply apply one of the formulas that we've derived before. we've got 4 resistors, and looking at the topology of them, what we have here is 2 resistors in series, a 500 ohm and a 1K, going to B, and also in parallel with those two resistors in series down here, a 500 ohm and a 1K. And now we have to apply our formulas iteratively. First stage, notice that these 2 resistors are in series, and therefore we can replace them with a single equivalent resistor which has the sum of those 2 values. So we could replace those 2 with just a single 1K5 resistor. Secondly, these 2 resistors are in series as well, so we can replace them with a single equivalent resistor which is also 1K5, 1000 plus 500. And now we've got 2 resistors in parallel. 2 resistors in parallel, we know the formula for that, and in the special case where the 2 resistors have the same value, the equivalent resistance is half of the individual resistances. Half of 1500 is 750. So our final equivalent circuit would look like this. A single 750 ohm resistor. Just check that works as well. Okay, I'll set this to 750 ohms. And yes, exactly the same current is flowing through for the same voltage being placed across it. Right, and now another slight variation on that one. This one. Notice the difference? The only thing that I've added is a wire from here to here. So I've now got this one. This is my new circuit. Okay, I can no longer analyze it the same way because I don't have any resistors in series. Have to start thinking about this in a different way. What I do have in this circuit here, however, are 2 resistors here in parallel. So 1K resistor, this side of this resistor and this side of the 500 ohm resistor are connected together. Over here, this side and this side of these resistors are connected together. These 2 resistors are in parallel. And I know the formula for 2 resistors in parallel. The one I usually use is the equivalent resistance is the product of the resistances, 1K times 500, divided by the sum of the resistances, which in this case is 1500 or 1K5. What's that? Well, 1000 times 500 divided by 1K5, 333.3, etc. ohms. So I can replace these 2 resistors with a single resistor with a value of 333.3 ohms. And I can do exactly the same thing with these 2 resistors on this side. These 2 are in parallel as well. They have the same values, 1K and 500 ohms, so they must have the same equivalent resistance, 333.3 ohms. And now I have 2 resistors in series. So I can apply the resistors in series equation, just add them up, and I've got down to a single equivalent resistance, 666.6 recurring ohms. So that is now the new equivalent resistance. I've added a wire and I've effectively reduced the equivalent resistance from 750 ohms to 666.6 ohms. Just check that works as well. Set this to 666 point lots of 6's, and yes, both of the currents are the same. For the same voltage across this resistor network, we're getting the same current through as we do for a single 666.6 so on resistor. and that would be true no matter what voltage we put across the two resistors. That's the whole point of having an equivalent resistance. It's always equivalent, it always behaves the same. Okay, final one to have a look at this time. This one. The same principles apply. We just go through it stage by stage, reducing the circuit using the resistors in series and resistors in parallel equations until we get down to a single resistor. Let's have a go. First thing to note is that this 1K resistor here and this 500 ohm resistor here are in parallel. Left hand side is connected together, right hand sides are connected together. So we can get rid of this 1K and this 500 ohm resistor by replacing them with a single resistor given by the parallel combination of 1K and 500 ohms. And we already know what that is, we just worked it out before. It's 333.3 etc. recurring ohms. So if I do that, then I can redraw this circuit in this form. That's a 2K, that's a 1K, that's a 500 ohms, there's a 3K down here, and I'm going to replace this parallel combination of a 1K and a 500 with a single 333.3 etc. ohm resistor before it leaves the network and goes out to point B. Next, well, these two resistors are in series. So we can replace them with a single resistor which has a value of 1K5. And that reduces my network to this. 2K, 1K5, 3K, 333. Now, I could just treat these two resistors as a parallel combination, replace them with a single resistor, and then that new resistor would be in parallel with this resistor. I could replace that with a single resistor and then combine it with this series resistor. But instead, since I have three in parallel and it will save a little bit of time, I will use the formula for three resistors in parallel. And that is, the equivalent resistance is 1 over R1, in this case 2K, plus 1 over R2, in this case 1K5, plus 1 over R3, in this case 3K. And that, if you work it out, is 1 divided by 1 over 2K, plus 1 over 1K5, plus 1 over 3K, which gives you 666.7, or strictly speaking 666.666 recurring ohms. So I now have a network which consists of 666.6 recurring ohms followed by a resistance of 333.3 recurring ohms. Those two are now in series. I can combine them using the formula for two resistors in series, which just means add them up. If I add up those two, I would end up with 1K. So, my maths predicts that this network should behave exactly the same as a 1K resistor. Let's check. Yes, it does. Put 10 volts across this network, 10 milliamps flows through, which is exactly what would happen through a 1K resistor. Excellent. Okay, that's all I wanted to chat about this time. Next time, we're going to be looking at a rather harder example, one that you cannot solve just by simply applying the formulas for resistors in series and resistors in parallel, because there are some resistor networks which cannot be solved in this way.